Hello everyone, welcome to lecture 5 of environmental chemistry. In this lecture we're going to cover the practical aspects of thermodynamics, building upon what we've learned in the previous lecture on the fundamentals of thermodynamics. So specifically in this lecture we're going to use thermodynamic relationships to estimate energy-related parameters of reactions. We're going to discuss energy-related parameters as the reaction progresses. So basically introducing the extent of reaction parameter and also evaluate the equilibrium constant at different temperatures. So something that we briefly discussed in the lecture that we described equilibrium constant, and now we want to elaborate on that quantitatively to see how specifically K is related to temperature. So I think we're going to rely heavily on the equations we had in the previous lecture. So it's good to overview some of the key concepts we had in the previous lectures, just to make sure that we know how to use specific equations, basically. So we talked about some energy-related parameters in the previous lecture. So we introduced the concept of system. So basically just a system is a boundary that is a piece of the universe. And then we mentioned that system can do work on the environment, or we can apply work to the system, and then the system can also exchange heat. And we talked about the internal energy. And then we mentioned that the internal energy are a combination of microscopic and macroscopic energy. And then measuring that would be very difficult. It requires a lot of information about the system. But then change in the internal energy can be measured, or it's something that we can play with. So that is a combination of heat and work exchange of the system with the surrounding. So basically delta U, the change in the internal energy, is how much is exchanging heat and work. And then we introduced the concept of enthalpy, H, and then we mentioned that basically H is the internal energy plus that PV, how much it takes to make that system, to the boundaries of the system. And then we show that based on the first law of thermodynamics for most of the environmental system of interest, because delta V is equal to 0, is at the same pressure. So therefore, the change in the enthalpy is equal to the change of the heat exchange of the system with the surrounding. And then we also introduced the concept of entropy. So, or S. And then we mentioned that we can change for any change. It results in the change of entropy of the total or the universe, which is basically a combination of the change in the entropy of the system plus the entropy change of the surrounding. We mentioned that the change in the entropy of the surrounding is a relatively complicated factor. So system is pretty straightforward. We were looking for something that we could relate these surrounding feature to something that is a system feature, that then we can collectively talk only about the system. And we use the first law of thermodynamics to basically derive this equation. The change in the entropy of the surrounding is equal to the change in the enthalpy of the system divided by the temperature. So this is basically, it makes it pretty useful, pretty straightforward in terms of now that we have all system levels. So combining these two together, we mentioned that minus T delta S of total is equal to the change in the enthalpy of the system minus T, the change in the entropy of the system. Again, all system levels. And then we mention, based on the second law of thermodynamics, for any process to be spontaneous. That should result in the change of the entropy of the universe to be greater than 0. So that would be for a spontaneous process. And then we define the last thermodynamic term, which was basically the Gibbs energy. So, or G. And this was basically a very nice trick to avoid working with delta S of the total. So we combine these factors into one, and then we call that delta G, or the change in the Gibbs energy. And from now on, we are only talking about the system, but delta H minus T delta S. A very known relationship that you've seen it probably before in general chemistry or thermodynamics. And then for the spontaneous process, delta G has to be less than 0 for the spontaneous process, because delta G is literally T delta S, and then T is in Kelvin, always greater than 0. So this to be, for delta S greater than 0, this factor, which is delta G, has to be less than 0 because of this minus factor and the fact that T is always positive. So this was general terminology we defined for by combining the first and the second law of thermodynamics. Then we went further and we talked more specific about different types of Gibbs energy, basically. So we specifically talk about the elements of the system and reactions. So two things that we're going to see later also is first to distinguish whether we're talking about species or we're talking about reaction. So, and then expanding G or delta G for either species or reaction. So what we had in the previous lecture for species, let's say species I, which is something that we have in the system, we can associate some G values for the species I, and then we define the chemical potential associated with the species I, so mu of chemical for I, or we define the molar Gibbs energy, or G molar of I. So qualitatively speaking, this means that if we add or remove 1 mole of one mole of I, how does the total G would change? So that's basically the description of the molar Gibbs energy of species I. And quantitatively speaking, we had this I to be Gi per mole, the molar one, which is based on the definition, is how much G would change if we add or remove 1 mole of I. And then we can basically expand this to be the total G related to species I is basically per mole times how much mole we have. So this would be basically per mole, and this is mole. So per mole times mole would be the total. And then the total G of the system, combining all the species now, would be basically Gi molar Ni, combining for all the species. And then we talked about basically how delta G for a species per mole is related to its delta H per mole and delta S for that species. Again, this is similar to the general description of delta G, delta H, and delta S that we had in the previous page. And then we talked about the standard condition to define sort of a baseline for Gi per mole, molar Gibbs energy. And then that standard condition, it's easy to find the values for that. And then we define that to be Gi per mole at the standard condition. And then we mentioned that for any GI at non-standard condition per mole, this is basically just a deviation from the standard condition, considering the activity of species I. Again, this is activity and not the concentration. So we need to do a little bit of calculation to deal with the activity and the activity coefficient. Basically, lecture 2, if I'm not mistaken, lecture 2, we covered that. So that's all about species, how one species is behaving or reacting in a system, and how the associated G value would change, whether we're at the standard condition or we're not, we're at a random condition. But then we expanded this for reactions. So the reaction basically is just the relationship between species. And then when we zoom in on the system, this is basically a relationship between different species. So we expect this to be, the relationship here to be similar to what we had for species. So this A and B could be basically this I and J. So for the reaction, we mentioned that delta G of the reaction, the molar delta G, is a combination of all the GIs molar, considering their stoichiometric coefficient. So this was how to calculate delta G of reaction. Then the same thing would be basically for delta H of reaction. And then delta S of the reaction would be how we combine the individual species to make the reaction variables. And then we talked about the fact that this would be the same for delta G of reaction at the standard condition, the same for delta H and delta S. So again, the same logic here applies. And then we talked about how delta G and delta H and delta S are combined and related to each other. Again, this follows the same relationship we had before. So delta H of reaction per mole is T delta S of reaction, similar to species and similar to the general form. And then we mentioned that this is also true at the standard condition. So delta H minus T delta S at the standard condition. And the last thing we mentioned in the previous lecture was for delta G at any condition, we can also calculate it based on the delta G of reaction at the standard condition plus some deviation, which was ln Q, the reaction quotient. Again, very, very similar to what we had for species. And then we talked about the fact that at equilibrium, delta G is 0. And then if we rearrange this, considering that Q in the equilibrium is K, then we get to this relationship. Delta G R at the standard condition would be equal to minus RT ln K. So this was how we calculate the equilibrium constant, this time from the delta G expression. So this was basically all the useful equation we drove in the previous lecture. So these are sort of the fundamental equations that we're going to use in this lecture. So first, solving a few problems to get used to, and more importantly, how to use and which equation to use here for species or reaction. And then later expanding a little bit beyond these fundamental equations and making it a little bit more practical. So moving on with example 1. In this example, this would be pretty straightforward. We're going to calculate the molar Gibbs energy of calcium. So we have 2 water samples. They were taken from 2 different lakes. The concentration of calcium in both samples are 10 to the minus 3. So The concentrations are equal. But then the two lakes have significantly different ionic strength. So that means the effective concentration of calcium, even though the concentration is the same, might not be the same. So that means the activity of these two won't be the same. So for one lake, we have the activity coefficient of 1, so that we can, assuming that's ideal. But for another lake, the activity coefficient is 0.5. So now we want to calculate the molar Gibbs energy of calcium. So molar Gibbs energy of calcium in each lake. Most likely we are not at the standard condition, so this is non-standard. And then we have the information about the standard condition, the temperature, R, and so on. So again, we have two different lakes, the same concentration of calcium. What's the associated Gibbs free energy of calcium in each lake? So the difference, as we mentioned, these are the difference in the activity or the effective concentration of calcium. So first, looking at the equations that we had in the previous page, first of all, we have to go for species. We're not dealing with a reaction. It's just one single species, which is calcium. And then we want to calculate the Gibbs free energy at a given condition. And what we have is the standard condition, and then basically the rest, the deviation from the standard condition. So this would be the formula that we need to pick. So G of calcium at that given condition is G of calcium at the standard condition plus RT ln of the activity of calcium 2+. And from lecture 2, we know that the activity is related to the activity coefficient and the concentration. So this would be the activity of coefficient of calcium plus the concentration of calcium 2+. So this is just the expansion of the activity. And now what we need to do is just for lake 1 and 2, the only difference is basically the activity coefficient. So for lake 1, we have the activity coefficient of calcium to be 1. So we're assuming this is pretty dilute, the ionic strength is pretty low, so we're assuming this to be sort of an ideal solution. So G of calcium 2+ is equal to the G0, which is this value. Just again, keep in mind the units basically. Here's in kilojoule, so 553.54 kilojoule per mole, plus now R is in the form of joule per mole per Kelvin. So we need to convert joule to kilojoule, or before we could convert kilojoule to joule, but it would be easier to work with converting joule to kilojoule. So 8.314 10 to the minus 3 kilojoule per mole per Kelvin times temperature. Again, this is in Kelvin, so 25. This would be 25 plus 273. That's the conversion from Kelvin to Celsius, or Celsius to Kelvin. So this would be 298 Kelvin times ln activity is 1, and then the concentration is 10 to the minus 3. It's good to check the units to just make sure they match. So this would be kilojoule per mole, this would be kilojoule per mole, Kelvin, but Kelvin will be simplified, and we know this is basically unitless. And when we do the calculation, we have minus 570 minus 570.65 kilojoule per mole. This is for lake 1. For lake 2, everything would be the same except calcium, the activity coefficient would be 0.5. And then G that we calculate The only factor here, we need to do 0.5 10 to the minus 3 instead of 10 to the minus 3. Then this would be minus 572.37 kilojoule per mole. So sort of similar to Lake 1, a little bit deviated from that, and then deviated also from the standard condition. Again, just showing the same concentration of calcium for the same species of calcium ion. It's the Gibbs, the molar Gibbs energy associated with this ion could be different in different systems. Here, the only difference between the two was how much ionic strength we have in different media. So how much activity suppresses basically compared to the ideal solution. Okay, so let's move on to the second example. So in the first example was all about the species. So in the second example is all about the reactions. And reactions, as we know, is relationship between different species. So it's all about carbon dioxide dissolution. We have this reaction of CO2 be hydrated with water to form carbonic acid. And then we have the temperature, it's 25. And then we have all the information about H, S, G at the standard condition per mole. So we can basically have delta G, delta S, and delta H of reactions pretty easily. And we have the reaction, so we have the activity, stoichiometric coefficient. And this is a balanced reaction, so the stoichiometric coefficient are basically 1. If this wasn't a balanced reaction, you need to first do the balanced reaction, so that stoichiometric coefficient is for a balanced reaction. So now the first part is simply calculating delta G, delta H, and delta S at the standard condition per mole. And we know this is pretty straightforward. Based on the relationship we had, we know delta G of reaction at the standard condition for reaction is basically a combination of all the GIs for the species involved. Keep in mind the stoichiometric coefficient for the reactants are negative, and for the product is positive. So this would be -1, this would be -1, this would be +1. So we start from CO2. So minus 1 times G of CO2. So minus 394.4 minus the value for H2O, which is minus 237.2, plus 1 times the value for carbonic acid, 623.2. Then this would be 8.4. The unit for all of them is in kilojoule per mole. So the unit for the overall would also be in kilojoule per mole. So now we can do the same thing for delta H. So delta H of R at the standard condition is basically the stoichiometric coefficient HI at the standard condition. So minus 393.5 minus 285.8 plus minus 699.6. The units are in kilojoule per mole, so the unit of the overall, which is minus 20.3 kilojoule per mole. So the same thing also for delta S would be basically the same expression of delta S and how that's related to the individual as delta H and delta G. So this would be minus 213.6 minus 69.9 plus 187. This would be minus 96.5 But now keep in mind the unit is joule per mole per Kelvin, not kilojoule. So later we're expecting sort of unit conversion if we want to combine delta S and delta H and delta G. So this would be all the values at the standard condition. And now the next part is asking to verify your delta G calculation. So far, what we did was delta G driving delta G from the individual species, but we know delta G is also related to delta H and delta S through a relationship that we had. We just want to confirm we get to the same delta GR at the standard condition if we drive it from delta H and also delta S. So delta H, we calculate this to be minus 20.3 kilojoule per mole. I'm intentionally adding the units so you make sure you have the unit conversion. So T would be 298 Kelvin. And then delta S would be 96.5. And now 10 to the minus 3 kilojoule per mole per Kelvin. Again, intentionally adding that unit to show that this is, you need the unit conversion also. So then this would give us 8.46 kilojoule per mole. And when we look at the value, this is pretty close to what we calculated based on the individual species, 8.4 and then 8.46, but using two different approaches. So that shows basically these are like basically not independent, but rather well connected to each other. So far we calculated delta G, delta H, and delta S at the standard condition. And now the next part is to calculate the K value for the reaction. So a very important parameter for a given reaction. And we know how K value is related to one of the parameters we just calculated. So this would be minus RT, ln K. And then a little bit of rearrangement. This would be K is equal to exponential of minus delta GR at the standard condition divided by RT. And this is the expression for K, and the rest would be just plugging numbers. K exponential of minus 8.4 or 8446, whatever value you put here would be pretty similar. Joule per mole, R is kilojoule per mole, 8.314, 10 to the minus 3 kilojoule per mole per Kelvin times 298 Kelvin. Then this would give us 0.034. So that's the equilibrium constant for the dissolution of carbon dioxide to form carbonic acid. Very useful information, and later this helps us to relate the species activity at the equilibrium, basically. So now the next part would be to calculate the Gibbs energy of the reaction. So there's no standard, so that means at a given condition, we want to calculate delta G of the reaction. And what's the condition? This is the condition. So if the activity and if the concentration of carbon dioxide and carbonic acid are these values. So for calculating delta G of reaction at a given condition, which is non-standard condition, is basically a deviation from standard condition. One of the formula that we had, and the deviation is related to the reaction quotient. So what we had was delta G of reaction at any condition would be delta G of the reaction at the standard condition plus RT ln Q. And for the reaction we had, we can expand the reaction quotient, RT ln. If you look at the reaction quotient would be the product over the reactant. And RT, then this would be the activity of H2O the activity of carbonic acid over the activity of CO2 over the activity of water. We know the activity of water as the pure form is 1. So eventually it would be the activity of carbonic acid and CO2. So now we need the activity coefficient, but it's fair to assume that this is a dilute solution considering the low concentration. So these are very low concentration. Combined together, this would be 1.1 10 to the minus 3. So pretty low, like even in the very low range of Debye-Huckel. So it would be fair to assume, because the system is very dilute, the species behave ideally. So we get activity coefficient of equal to 1. Therefore, the activity is equal to the concentration for the species. And the concentrations are basically given. So the rest would be then delta GR, plug in numbers, then delta GR at the standard condition, 8.4 kilojoule per mole, plus RT, 8.314 10 to the minus 3 kilojoule per mole per Kelvin, times 298 Kelvin, then times Ln 10 to the minus 4, the concentration of carbonic acid to the concentration of carbon dioxide. And then this would give us 2.7 kilojoule per mole. So the Gibbs free energy of the reaction for this given condition deviated from the standard value of 8.4. So now the next part of the question is the reaction spontaneous at a given concentration? So if we blend this much carbonic acid and this much CO2, would the reaction progress in the way that it's written? So the way it's written is basically CO2 plus H2O is forming carbonic acid. So for that reaction, it's all about delta G of reaction. Obviously not the delta G of reaction at the standard condition. So this is bigger than 0. So this is not spontaneous. So this reaction won't progress because the progress of this reaction doesn't add entropy to the universe, so which is the foundation of the second law of thermodynamics. We can actually verify this by saying Q, which is 10 to the minus 4 divided 10 to the minus 3, which is 0.1, is not equal to K, which was 0.034. And since it's not equal to K, so it's not at equilibrium, and then it's bigger than K, so Q is bigger than K, and we know that if Q is bigger than K, the reaction is spontaneous in the reverse side. So it doesn't go this way, but it would be spontaneously going backwards. So the Q reaches the K value by going this way, this direction. So we have more carbonic acid forming CO2. So the two examples we had, the purpose was in the first one to show how to use the relationship we had for species, how to use them to estimate a value at a real world condition. And then in the second example was basically doing the same thing for reactions. So we learned how to use those fundamental relationships for species and reactions, and then how to gain information about the system of interest. But now we want to expand a little bit on what we had before, specifically delta G, and then introduce the concept of extent of reaction. So the extent of reaction, simply speaking, if we have A in equilibrium with B, if all of A is converted to B, so there's no B, so there's no A, it's all B, then we call that the extent of reaction of 1. So the extent of reaction is completed. So we are at the extent of 1. if there's no A, there's no B, and all of A is in its pure form, so there's no progress of reaction, there's no extent of reaction. So in that condition, we can say the extent of reaction is 0. And on the way from the extent of reaction from 0 to 1, which are the two extreme ends, there is the equilibrium. So the equilibrium represents an extent of reaction, which is somewhere between the two. And then going from an extent of reaction to the equilibrium extent of reaction, we're dealing with a dynamic delta G. So delta G is also changing. So one of the good practices is to trace how delta G is changing as a function of the extent of reaction. So the formal definition of the extent of reaction is the relative amount of reactants and product present in the system are sometimes represented in terms of the coordinate epsilon, called the extent of reaction. This coordinate has a value of 0 if the reaction has proceeded to the left, so basically that all A to B, all in the form of A, and then the extent of 1 is all the way to the right. So now we want to basically approach this through an example. So we had this reaction before in one of the lectures, and we mentioned that this is a very a good, important disinfectant reaction. And we mentioned that these two species that are in equilibrium, they have different disinfectant power, disinfectant effectiveness. So one has more disinfectant power. So we want to basically have that species more. If I'm not mistaken, it was HOCl. So now that we have some initial concentration of the two, so HOCl and OCl minus are these values. So most likely they're not at equilibrium. These are just random values that we initially have in the system. And then they approach the equilibrium. And we know the pH of the system is fixed, and then the activity of H plus is basically 10 to the minus 7. So the pH is fixed at 7. So giving the following thermodynamic data, plot delta GR, how delta G of the reaction changes as a function of the extent of the reaction for the dissolution of HOCl. The temperature is also given at 25 degrees C. And what we're giving also is GI at the standard condition for all the species. So what we need to have eventually is a relationship that is delta GR in one hand, and then some other factors then which we have epsilon in these factors. So if we get to that point, then we only change epsilon, and then we calculate delta G, then we can plot it. We can plot delta G of R as a function of epsilon, somehow changing, for example. So but the core is get to that point. We know delta G of reaction is a function of delta G of reaction in the standard condition plus RT ln of the reaction quotient. In this case, the reaction quotient is the activity of H plus, the product OCl minus, and then the reactant. So far we have sort of that relationship that we're looking for. In one hand, we have delta GR, something that we're interested, but in this case, we don't have that epsilon factor yet. So we need to basically somehow relate these to epsilon. So let's plug in some numbers, or let's just calculate delta GR at the standard condition. This would be pretty straightforward. We know this would be DI, similar to what we have for species and reactions. So it would be minus 79.9, that's for HOCl, plus minus 36.8 OCl minus, plus 0, which is for H plus. This would be 43.1 kilojoule per mole. Something that we need. And now we can plug in delta G0 into, so plug in this value here and then rewrite this one. It's also, we can easily assume that this is ideal solution because of the low concentration and no information about the ionic strength, so we assume that the activity coefficient is 1, so the activity and concentration are equal. So then delta GR is equal to 43.1 kilojoule per mole, which is delta G0, plus 8.314, again turning it to kilojoule, times 298 Kelvin, times Ln. We know the activity of proton would be always 10 to the minus 7 in this case, in this particular example, then the concentration of OCl, and then the concentration of HOCl. A little bit of simplification. Delta GR is 43.1 plus 2.48 Ln of 10 to the minus 7 OCl minus over HOCl. So far, again, we have that delta G of interest, but here we don't have epsilon. So if we can convert the ratio of OCl minus to the ratio of HOCl to epsilon, then we can basically talk about, we have that the relationship that we're looking for. And obviously there is a relationship between OCl and HOCl with epsilon, because epsilon is the extent of reaction. The extent of reaction dictates the individual species and also the ratio of the individual species. So let's put it this way. So our job would be how these two are related to epsilon. If we can do that, then delta G is related to epsilon eventually. So let's look at what is the maximum possible value for HOCl or OCl minus. So the maximum value is when all the HOCl is converted to OCl minus. That's the maximum value for OCl minus, and the minimum value for OCl minus would be 0, HOCl. And then the maximum value for this guy would be when all of OCl minus is converted to HOCl, plus the amount of obviously HOCl that we initially had. So the maximum value would be 10 to the minus 4 plus 10 to the minus 3. The maximum value of this one plus this one. That would be the extent, the far extent of the either side. All of this is converted to this, so all of that 10 to the minus, what was 10? Yeah, HOCl was 10 to the minus 3. So let's assume all of this is converted to HOCl. Then we had 10 to the minus 3 of that. 10 to the minus 4 is also converted. So eventually we get the combination of the two, which would be 1.1 10 to the minus 3 molar. So that's the max of either of these two. So we know at epsilon of 0, so that means no progress of the reaction. So there's no HOCl converted to OCl minus. So in that case, HOCl is at the maximum condition, which is 1.1 10 to the minus 3 molar, and OCl minus, the concentration is 0. So no extent of reaction. And on the other side of the spectrum, E epsilon 0, then we get the opposite case. HOCl is 0, and then OCl minus is equal to 1.1 10 to the minus 3. So a condition that satisfies these two, or at this condition, would be, we can say OCl minus is 1.1 10 to the minus 3 times epsilon. Just do this. Epsilon equal to 0. You put it here, this would be 0, which is the case here. Do this one. Epsilon is equal to 1, put it here, then the OCl minus would be 1.1 10 to the minus 3, which would be the case also here. And similarly, we can say HOCl is 1.1 10 to the minus 3, 1 minus epsilon. So the other side, exactly opposite. So now we have these two species as a function of epsilon. So the only thing is we insert or plug in these two into this relationship. So if we do that, then we have everything we need. So into delta GR, then we get delta GR to be 43.1 plus 2.48 ln 10 to the minus 3 times 1.1 10 to the minus 3 epsilon. So that's OCl minus. And then HOCl minus is 1.1 10 to the minus 3, 1 minus epsilon. We can do a little bit of simplification here. Then eventually we get to delta GR to be 43.1 plus 2.48 ln of 10 to the minus 7 epsilon divided by 1 minus epsilon. That's the overall reaction, the overall equation that we need. The rest would be pretty straightforward. Our y-axis is delta GR. Our x-axis would be epsilon. And then we need to just plot this one. So that means we go to an Excel file. We insert some epsilon we give it 0. We calculate delta G. We give it like 0.1. We calculate delta G 0.2 and then so on. Eventually, we can have a plot of delta GR as a function of epsilon from 0 to 1. And if we do that in Excel, eventually we get to this figure. Or maybe not this one. Eventually get to this one. Yep. So as you see, this is how delta G is changing as a function of the extent of the reaction. Now we can look at some important factors. We know delta G is equal to 0 at equilibrium. So this is delta G at equal to 0. And we know this is equilibrium. And then we can calculate the epsilon of equilibrium to be roughly 0.2. So this is equilibrium. And then based on the given concentration, we can also calculate the delta G of initial, the extent of initial, which would be OCl minus of initial divided by 1.1 10 to the minus 3. So basically relying on this one. So this would be 10 to the minus 4, 1.1 10 to the minus 3, or roughly 0.09 or 0.1. So this would be somewhere here. So this is delta G of initial and epsilon of initial. Again, very important figure. And then we did the same thing for basically equilibrium. We know at equilibrium, delta G of reaction is 0. And E of equilibrium was 0.2. So dynamically, how delta G is changing from the initial condition here to the equilibrium. So if we let this system run, it goes from here all the way to here. So, this delta G all the way to delta G of 0. But it could be at any point between 0 and 1. If we pick any point here, eventually it ends up at the equilibrium. So it really doesn't matter where we start. Eventually it ends up at the epsilon of 0.2 in this particular example. Okay, so now let's move to the third part of the lecture, which is also the last part of the lecture, which is how the equilibrium constant K would change as a function of temperature. So when we talked about equilibrium constant in lecture 3, if I'm not mistaken, we mentioned that it makes sense if we say this is something related to the temperature of the system, so it could be temperature dependent. And now we have enough relationship for K value that the T factor shows up here and there. For example, K we connected to delta G, and delta G is connected to delta G0, and delta G0 is connected to delta G, and delta G is somehow connected to temperature through other relationships. But now we want to see how we can have a mathematical derivative or a mathematical expression to connect K to something that is known or something that is constant, and also something that we can rely on to calculate K at different temperatures. So now we know K value is related to delta GR at the standard condition minus RT ln K. We know also delta G0 is also delta H R minus T delta S. Be very, very careful. Delta GR at the standard condition is temperature dependent, as you see here. But these two are temperature independent. So these are the factors, the thermodynamic feature. This is something that we define basically. So even at the standard condition, this is temperature dependent. These two, temperature independent. So if we combine the two, we get to minus delta H R divided by T plus delta S R to be R ln K. So this relationship is pretty useful. It does the job to calculate K value at any temperature using temperature independent parameters. But the problem with this one is that we don't know much about the entropy of the system and the change in the entropy of the system. So if we can somehow get rid of this entropy factor and relying on delta H, because we know delta H is eventually related to Q, then it would be more straightforward to play with. So one trick would be to use the derivative, how two sides are a function of temperature. So the derivative of these two sides, so dt, d over dt of the left side minus delta H R T plus delta S R, and then d over dt R ln K. Do a little bit of rearrangement. So here this can be applied to both. So this is not temperature dependent as we mentioned. So basically this would be d. So d over dt of this guy would be equal to 0. So that makes it a little bit simplified. So here we also know delta HR, also not a function of temperature. So this can come out d over dt of 1 over t. And in this side we got R, which is not temperature dependent, of ln K, which is temperature dependent. For a little bit of rearrangement, minus delta H R divided by R, d over dt of 1 over t, and then here d over dt of ln K. Now this one we can do the integral from t1 to t2, and then on the left side and on the right side k1 and k2. So this is the K value at temperature 1, the K value at temperature 2. And if we do the derivative, then eventually what we get is delta HR divided by R, 1 over T1 in Kelvin, 1 over T2 equal to ln K2 over K1. And this is called the Van Hoff equation. A very useful relationship that describes basically what would be the K value as a function of temperature. Let's say you have the K value for the room temperature, so K1 at room temperature of 2098. Then you can calculate K2 at any given temperature if you know what's the delta HR of the reaction at the standard condition, which is T independent. So it's not a function of T. So this relationship would be very straightforward. And then the good thing about this relationship, there's no delta S involved. So you don't need any information about delta S. It's only relying on delta H, which can be easily measured or quantified using the heat exchange of the system with the surrounding, basically. So this is how we get from this relationship to something that is more practical, which has K1, K2, T1, T2 without any delta S using this derivative we mentioned. So we do a quick example through calculating the equilibrium constant at an elevated temperature of 90 for the same reaction we had. So we had the absorption or dissolution of CO2 into water to form carbonic acid, and what we had in the previous lecture, in the previous example, was the K value at 25 C. And now we want to calculate the K value at 90. First, we can do the approach of Gibbs energy. So it's specifically asking us to do Gibbs energy. So to do that, we know delta GR at 90 is equal to minus RT ln K. And at the same time, delta GR at 90 is equal to delta HR. It doesn't matter if it's 90 or 25, this is temperature independent, delta SR. So we just specifically mention that these two are T independent. But this guy is temperature dependent. So since these two are temperature independent, we can get it from the value that we had in the other example, minus 20.3 kilojoule per mole. This is what we calculated in the other example. And then delta S of R, we also calculated this to be minus 96.5 joule per mole. Again, be very careful with the unit. So using these two, we can calculate delta GR at the standard condition at 90 to be basically minus 20.3 kilojoule per mole minus T 298. Sorry, not 298. This would be 363. This would be 273 plus 90 C, 363. Kelvin times minus 96.5, 10 to the minus 3 kilojoule per mole per Kelvin. So this would be also Kelvin. Eventually, this would give us 14.7 kilojoule per mole. If you remember, this was 8.4 kilojoule per mole. And now we can have this inserting here to calculate the K value. So K at 90, this would be the exponential of minus delta G R standard at 90 divided by RT, and then plug in numbers. This would be 0077. And if you remember, this was 0.034. So it's changing basically. And we were able to calculate it based on the fundamental relationships. And now we can do the same thing using Van Hoff equation. Again, Van Hoff, the good thing about Van Hoff, it's not it doesn't involve delta S. But here we were lucky that we had delta S, but it's not the case all the time. So in part B, we want to do Van Hoff for ln k2, or let's call this k at 90, divided by k at 25 would be equal to delta H R standard divided by R, 1 over T1, T25, minus T2, T90. In T25, that means 298 Kelvin. T90, that is also 363 Kelvin. We had K at 25 to be 0.034. K at 90, this is something that we don't know, and we're relying on the Van Hoff to calculate it. So doing a simple Van Hoff, K at 90 divided by K at 25, this would give us minus 1.47, or K at 90 would be 0.0078. And as you see, this is very, very close to what we had using the fundamental relationships here. So this was based on the fundamental relationship. We got to this value, but now we get to this value using Van Hoff. So both values are very close to each other. Just highlighting how Van Hoff could be pretty useful. So to wrap up the lecture, what we talked about was looking at three different things. One was using delta G R, or expansion of what we had in the previous lecture, and use it for real world examples. Then we talked about how delta G R changes at different reaction progresses, or different epsilons. And then at the end, we looked at the equilibrium constant as a function of different temperature. And we introduced the concept of Van Hoff equation. A pretty straightforward relationship to look at how to calculate K at different temperatures. And these are the relevant readings coming from the main textbook. And then this was the last lecture of chapter 1. In the next lecture, we're going to solve some problems, problem solving, all quantitative and sometimes some touches of conceptual problems, and to make you ready for the exam which comes after problem solving section. Thank you.